March 21, 1941. RAF Biggin Hill, Kent. 23-year-old squadron leader Robert Stanford Tuck pushed his Spitfire into a steep dive, chasing a Messerschmitt Bf 109 across the English Channel. At 300 miles per hour, Tuck had the German fighter in his gun sight when something extraordinary happened. For the first time since the Battle of Britain began, his Merlin engine continued running smoothly as he pulled negative G-forces in the dive. No black smoke. No engine cutout. No momentary hesitation that had cost so many RAF pilots their lives over the past 8 months. What Tuck didn't know was that his Spitfire carried a small brass disc, barely larger than a coin, welded into his fuel line. The device looked like nothing more than a bent nail hole punched through a metal washer. Aviation historians would later call it the most important modification in RAF history. Pilots knew it by a more colorful name that honored its inventor, a remarkable woman who had solved the Spitfire's most dangerous flaw with engineering brilliance that bordered on genius. This is the story of how Beatrice Schilling's orifice restrictors saved the Royal Air Force during its darkest hour. Her solution transformed the most famous fighter aircraft in history from a beautiful but fatally flawed machine into the weapon that would help win the Battle of Britain. What appeared to be a simple engineering fix represented a revolution in aircraft fuel systems that would influence aviation design for decades to come. The crisis that threatened to ground the RAF's most important fighters didn't begin with enemy action. It started with a fundamental flaw in the Rolls-Royce Merlin engine that powered both the Supermarine Spitfire and Hawker Hurricane. When these aircraft performed negative G-force maneuvers, diving nose down to attack German bombers or evade enemy fighters, their engines would suddenly lose power at the most critical moments of combat. The technical explanation was deceptively simple. Early Merlin engines used dual-choke updraft SU carburetors that relied on gravity to feed fuel from a float chamber into the engine's intake system. During normal flight, fuel remained at the bottom of the chamber where it could flow through jets into the airstream. However, when an aircraft pitched nose down and pulled negative G-forces, fuel was forced to the top of the chamber, away from the jets, causing immediate fuel starvation. If the negative G-forces continued, the situation became catastrophic. Fuel collecting at the top of the float chamber would force the float to the bottom, opening the needle valve completely. This flooded the carburetor with an over-rich fuel mixture that drowned the supercharger and caused complete engine failure. Recovery required several seconds of level flight to clear the flooded system, time that RAF pilots rarely had during combat. German fighter pilots quickly recognized this vulnerability and exploited it ruthlessly. Messerschmitt Bf 109. Fighters used direct fuel injection systems that functioned normally regardless of aircraft attitude. When pursued by RAF fighters, German pilots would pitch nose down into steep dives, knowing their opponents could not follow without losing engine power. The telltale puff of black smoke from a Spitfire's exhaust became a signal for German pilots to press their attack. RAF Fighter Command attempted to counter this disadvantage through tactical modifications. Pilots learned to perform half rolls before diving, maintaining positive G-forces that kept fuel at the bottom of their carburetors. This workaround allowed pursuit of German aircraft, but added precious seconds to every engagement while reducing the surprise factor that made fighter attacks effective. Many RAF pilots died while executing these complex maneuvers under fire. The woman who would solve this life-threatening problem seemed an unlikely savior for the Royal Air Force. Beatrice Schilling was born March 8, 1909, in Waterlooville, Hampshire, the daughter of a butcher who encouraged her mechanical interests despite social conventions that discouraged women from engineering careers. Young Beatrice spent her pocket money on tools and Meccano construction sets, displaying the hands-on problem-solving approach that would later save countless pilots' lives. Schilling's unconventional path to prominence began with motorcycles. As a teenager, she raced motorcycles successfully at Brooklyn Circuit, becoming one of only 3 women to earn the British Motorcycle Racing Club Gold Star for lapping the track at over 100 miles per hour. Her mechanical expertise extended beyond racing as she modified and maintained her own machines, developing the intuitive understanding of engine behavior that would prove crucial during the war. Academic achievement complemented her practical skills. Schilling earned a bachelor's degree in electrical engineering from Manchester University, followed by a master's degree in mechanical engineering. Her combination of theoretical knowledge and hands-on experience caught the attention of the Royal Aircraft Establishment at Farnborough, where she was appointed as a scientific officer just before the outbreak of World War II. The Royal Aircraft Establishment represented the pinnacle of British aviation research, tasked with solving the technical problems that emerged as aircraft performance pushed the boundaries of existing technology. When war began in September 1939, Ray's mission became urgent and personal. Every engineering failure meant dead aircrews and lost aircraft that Britain could not afford to replace. The pressure to find solutions was immense, and conventional approaches were proving inadequate. Schilling's assignment to carburetor research placed her at the center of the RAF's most critical technical problem. Reports from Fighter Command described engines cutting out during combat maneuvers, but initial investigations focused on fuel quality and carburetor adjustment rather than fundamental design issues. The scope of the problem became clear only as combat reports accumulated throughout summer 1940. The Battle of Britain's opening phase exposed the Merlin carburetor flaw as a strategic vulnerability that threatened RAF effectiveness. German intelligence recognized that British fighters could not follow diving attacks, information that spread quickly through Luftwaffe units. Fighter Command's tactical reports documented dozens of engagements where RAF pilots had German aircraft in their gun sights, only to lose them when engine power failed during pursuit dives. Air Chief Marshal Hugh Dowding, commanding RAF Fighter Command, understood that technical problems could prove as dangerous as enemy action. Britain's fighter strength was limited, and losing aircraft to avoidable mechanical failures was strategically unacceptable. Dowding pressured the Air Ministry and aircraft manufacturers to find immediate solutions, but complex engineering problems rarely yielded to administrative demands. Rolls-Royce engineers approached the carburetor problem through conventional channels, designing improved float chambers and modified needle valves that would reduce flooding effects. These solutions required extensive testing and production modifications that would take months to implement. Prototype installations showed promise, but could not be manufactured quickly enough to affect the ongoing battle. Fighter Command needed an immediate fix that could be applied to existing aircraft without removing them from service. Schilling recognized that conventional solutions were too slow and too complex for wartime implementation. Her motorcycle racing experience had taught her that simple modifications often proved more effective than elaborate redesigns. Racing engines faced similar fuel delivery problems during rapid acceleration and deceleration, problems that racers solved with basic restrictor devices that limited maximum fuel flow. The breakthrough came when Schilling analyzed the specific fuel flow requirements of the Merlin engine under combat conditions. Maximum power output required a precise fuel-to-air ratio that carburetors achieved by allowing unrestricted fuel flow from the float chamber. However, this same unrestricted flow caused flooding during negative G maneuvers. Schilling realized that limiting fuel flow to exactly the amount needed for maximum power would prevent flooding while maintaining full engine performance. Her solution was elegantly simple. Schilling designed a brass restrictor with a precisely calculated orifice that allowed fuel flow sufficient for maximum power, but prevented the excessive flow that caused carburetor flooding. The device resembled a thimble initially, later simplified to a flat washer with a calibrated hole in the center. Most importantly, the restrictor could be welded into existing fuel lines without removing aircraft from service. Testing the restrictor required careful calculation of orifice dimensions for different engine configurations. Merlin engines operated at different boost pressures depending on their application, requiring restrictors calibrated for 12 pounds per square inch manifold pressure on standard engines and 15 pounds per square inch on supercharged variants. The orifice diameter had to be precise within thousandths of an inch to achieve proper fuel flow characteristics. Initial tests at Farnborough demonstrated the restrictor's effectiveness, but also revealed its limitations. The device prevented carburetor flooding during quick negative G maneuvers, allowing pilots to dive on enemy aircraft without losing power. However, sustained inverted flight remained impossible because the restrictor could not solve the fundamental problem of fuel flowing away from carburetor jets during prolonged negative G exposure. The testing protocol required meticulous documentation of every flight trial. RAF test pilots conducted systematic evaluations using different restrictor configurations, measuring engine response times during various negative G scenarios. Flight Lieutenant Humphrey Edwards Jones, chief test pilot at Farnborough, reported that modified aircraft maintained consistent power output during diving attacks that would have caused engine failure in unmodified machines. Wind tunnel experiments complemented flight testing by providing controlled environments for measuring fuel flow characteristics. Engineers could simulate negative G conditions while monitoring carburetor behavior through transparent chambers that revealed fuel movement patterns. These tests confirmed Schilling's theoretical calculations and validated the restrictor's effectiveness across different flight attitudes and power settings. The most dramatic validation came during simulated combat trials, where modified and unmodified aircraft engaged in mock dogfights. Test pilots flying restrictor-equipped Spitfires could pursue diving targets aggressively, while pilots in standard aircraft had to abandon attacks when engines lost power. The performance difference was immediately apparent to observers and provided compelling evidence for widespread implementation. Production planning for restrictor installation required coordination between multiple organizations. The Royal Aircraft Establishment manufactured initial quantities, while civilian contractors prepared for mass production. Quality control procedures ensured dimensional accuracy within thousandths of an inch, critical for maintaining proper fuel flow characteristics. Each restrictor underwent individual testing before shipment to operational units. Fighter Command accepted these limitations enthusiastically. Combat maneuvers rarely required sustained inverted flight, but quick negative G transitions occurred constantly during fighter engagements. Eliminating engine cutouts during these critical moments would restore tactical flexibility that RAF pilots had lost to German fuel injection systems. The restrictor represented a crucial capability restoration, rather than a complete solution to all fuel system problems. Schilling's role expanded beyond design when Fighter Command requested immediate installation throughout the RAF. Rather than waiting for normal maintenance schedules, the modification program required visiting operational squadrons and installing restrictors on aircraft that might fly combat missions the same day. Schilling assembled a small team of technicians and embarked on a tour of RAF fighter stations that would become legendary within the service. The installation tour began in early 1941, prioritizing frontline squadrons facing daily combat operations. Schilling traveled between airfields on her motorcycle, carrying restrictors and welding equipment necessary for field modifications. The sight of a woman arriving at fighter stations to modify Spitfires and Hurricanes initially surprised RAF personnel, but Schilling's competence and the urgency of her mission quickly won acceptance. Each installation required approximately 30 minutes of work on an aircraft's fuel system. Schilling's team would locate the main fuel line between the tank and carburetor, cut the line precisely, and weld the restrictor in place, with connections that restored structural integrity. The modification appeared deceptively simple, but incorrect installation could cause fuel leaks or flow restrictions that would disable aircraft as effectively as enemy action. Squadron maintenance personnel watched closely as Schilling demonstrated proper installation techniques. The knowledge transfer was crucial because ongoing operations would require additional modifications as replacement aircraft arrived and existing machines needed service. Training RAF technicians to perform installations ensured the modification program could continue without requiring Schilling's personal presence at every airfield. Pilot reaction to the restrictor modification was overwhelmingly positive. Squadron leader Douglas Bader, commanding No. 2 Squadron, reported immediate improvements in combat effectiveness after installation. His pilots could now dive on German formations without fear of engine failure, restoring the aggressive tactics that had made RAF fighters effective during the early war period. The restrictor's battlefield impact became apparent within weeks of widespread installation. Combat reports from Fighter Command documented successful engagements where RAF pilots pursued diving German aircraft and maintained contact throughout negative-G maneuvers. German pilots found that their traditional escape tactic no longer provided guaranteed safety from RAF pursuit, forcing tactical adaptations that reduced Luftwaffe effectiveness. Statistical analysis revealed the modification's strategic importance. Fighter Command calculated that restrictor-equipped aircraft achieved significantly higher success rates during bomber interceptions compared to unmodified fighters. The improvement reflected not just individual combat advantages, but also increased pilot confidence that encouraged more aggressive engagement tactics when facing German formations. The device earned affectionate nicknames that reflected both its effectiveness and the RAF's irreverent humor. Officially designated the RAE restrictor, pilots called it Miss Schilling's Orifice, or simply the Tilly Orifice in honor of its inventor. Sir Stanley Hooker, the Rolls-Royce engineer who led supercharger development, coined the colorful nickname that became standard usage throughout Fighter Command. By March 1941, restrictors had been installed throughout RAF Fighter Command, transforming the tactical balance between British and German fighters. The modification program represented unprecedented cooperation between research establishments and operational units, demonstrating how engineering solutions could be rapidly implemented when military necessity demanded immediate action. Schilling's achievement became a model for wartime innovation that influenced subsequent development programs. The restrictor's success led to broader recognition of fuel system problems in military aircraft. Manufacturers began incorporating flow restriction principles into new carburetor designs, while research establishments investigated alternative fuel delivery systems that would eliminate gravity-dependent components entirely. The long-term solution emerged in 1943 with pressure carburetors that used fuel injection principles to maintain consistent flow regardless of aircraft attitude. Schilling's wartime contributions extended beyond the famous restrictor modification. She participated in numerous research projects aimed at improving aircraft performance and reliability, including work on engine cooling systems, fuel tank designs, and hydraulic components. Her combination of theoretical knowledge and practical experience made her invaluable for solving the complex problems that emerged as aircraft performance continued advancing throughout the war. The engineering principles underlying Schilling's restrictor influenced post-war aviation development in unexpected ways. Jet engines required precise fuel flow control systems that incorporated similar restriction concepts, while helicopter development faced unique fuel delivery challenges that benefited from lessons learned during the Spitfire modification program. The simple brass disc that saved RAF fighters contributed to engineering knowledge that shaped aviation advancement for decades. Personal recognition for Schilling's achievements came slowly but eventually reached the highest levels of British government. She received the Order of the British Empire for her wartime service, acknowledgement that her engineering work had strategic importance equal to combat achievements. The honor reflected growing recognition that technical innovation was as crucial to military success as traditional battlefield valor. Post-war career opportunities allowed Schilling to continue contributing to British aerospace development. She worked on the Blue Streak missile program, researched wet runway effects on aircraft braking, and participated in various projects that advanced understanding of aerospace engineering principles. Her career demonstrated how wartime innovations could transition into peacetime applications that benefited civilian aviation. Schilling's story became part of RAF tradition, taught to new generations of pilots and engineers as an example of how individual initiative could solve seemingly impossible problems. Her restrictor modification proved that elegant engineering solutions often appeared simple in retrospect, but required exceptional insight to conceive and implement. The lesson influenced military procurement policies that emphasized rapid problem-solving over bureaucratic procedures. The device itself became a museum artifact, preserved at the Imperial War Museum as evidence of British engineering ingenuity during the nation's darkest hour. Visitors could examine the simple brass disc that had helped save the Royal Air Force, understanding how seemingly minor technical improvements could influence major historical events. The restrictor represented the intersection of individual brilliance and national necessity that characterized Britain's war effort. Modern aviation historians recognize Schilling's contribution as pivotal to RAF effectiveness during the Battle of Britain. Without the restrictor modification, Spitfire and Hurricane squadrons would have remained vulnerable to German diving attacks throughout the crucial months when air superiority determined Britain's survival. Her engineering solution provided fighter command with tactical flexibility that proved decisive during critical engagements. Computational analysis using modern engineering tools has validated Schilling's intuitive design decisions. Computer modeling confirms that her orifice dimensions achieved optimal fuel flow characteristics for Merlin engine requirements, while preventing carburetor flooding under negative G conditions. The mathematical precision of her empirical solution demonstrated exceptional engineering judgment that anticipated principles later formalized through advanced analysis techniques. The restrictor's influence on aircraft design extended beyond immediate wartime applications. Modern fuel injection systems incorporate flow restriction principles that trace their development to Schilling's original concept. Electronic engine control systems use similar logic to prevent fuel system flooding while maintaining optimal power output under varying flight conditions. Her simple mechanical solution contained principles that remain relevant to contemporary aerospace engineering. Beatrice Schilling died November 18, 1990, at age 81. Having witnessed the transformation of aviation from mechanical simplicity to electronic sophistication. Her obituaries emphasized how a young woman's engineering brilliance had influenced one of history's most important military campaigns. The Royal Aircraft Establishment honored her memory by establishing research fellowships that encourage innovative approaches to aerospace engineering problems. Educational institutions now teach Schilling's story as an example of successful engineering problem-solving under extreme pressure. Her combination of theoretical knowledge, practical experience, and innovative thinking provides a model for contemporary engineers facing complex technical challenges. Students learn that breakthrough solutions often require abandoning conventional approaches in favor of simple concepts that address fundamental problems directly. The motorcycle racing champion who became an aviation engineer represents a unique figure in British technical history. Her willingness to challenge conventional wisdom, combined with hands-on mechanical expertise, enabled solutions that eluded traditional engineering approaches. Schilling's achievement demonstrated how diverse backgrounds and unconventional thinking could contribute to national defense in ways that purely academic training might miss. Contemporary feminist scholars recognize Schilling as a pioneer who succeeded in male-dominated fields through exceptional competence and determination. Her achievements predated formal efforts to encourage women in engineering careers, proving that talent and dedication could overcome social barriers when institutional need was sufficiently urgent. Her example inspired subsequent generations of women to pursue technical careers despite persistent discrimination. The simple brass restrictor that Schilling designed in 1941 continued serving RAF aircraft until pressure carburetors replaced updraft systems in 1943. Many restrictors remained installed even after superior fuel delivery systems became available, testament to pilots' confidence in the modification that had saved their lives during desperate battles over Britain. The device represented engineering elegance that achieved maximum effectiveness through minimum complexity. On March 21, 1941, when Squadron Leader Tuck's Spitfire maintained power throughout his diving attack, he experienced the transformation that Beatrice Schilling had made possible. Her bent nail fix had restored the RAF's tactical flexibility at the moment when Britain's survival depended on fighter command's effectiveness. The simple brass disc welded into a fuel line represented the engineering brilliance that helped win the Battle of Britain. That's how one engineer's orifice restrictor saved British aviation through innovative problem-solving that transformed flawed fighters into war-winning weapons. Beatrice Schilling's achievement demonstrated how individual technical excellence could influence strategic outcomes when engineering solutions met operational necessity during history's most critical moments.